Hello and welcome to the next lecture on terpenoids. Today we will discuss on abietic acid, which is a tricyclic diterpenoid. We will touch upon the following points: introduction of abietic acid, structure determination, UV visible spectra, which with the help of which we will assign the position of double bond. The introduction of abietic acid. It belongs to the resin acids of turpentine and widespread in conifers such as various pines, larch trees and firs. Melting point of abietic acid is around 172 to 175, the range of melting point. It is used in organic synthesis. It is one of the main ingredients of resin. Rosin acid ester is used as an ingredient for the preparation of paints, varnishes, soaps and plastic. This is the structure of abietic acid. You can see it is a tricyclic compound containing 3 rings. 2 double bonds are present and the ring here it is heteroannular diene. Isopropyl group is present at position 13. 1 angular methyl group at position 10. At the position 7 there is 1 methyl group and carboxylic group which is tertiary, which is present on tertiary carbon atom 4. Now we come to the structure elucidation of abietic acid, which is based on chemical analysis. On the basis of elemental analysis and molecular formula of abietic acid is assigned as C20S30O2. On the basis of this molecular formula, we reach to the following conclusions. First, as it contains C20 carbon atoms 20, so it is a diterpenoid. The isoprene units are joined in head to tail arrangement as usual according to special isoprene rule. The next important point is the double bond equivalence, which is given by the formula, and substituting with the values of x and y, we get total double bond equivalence equal to 6. This means either double bonds are present or rings are present or the combination of both are present. Now we come to the next point, which is what is the nature of this unsaturation. First, it is the abietic acid is subjected to hydrogenation in the presence of platinum and we get tetrahydroabietic acid. This means that it contains 2 double bonds, because as you can see from C30 it comes out to be C34, means 2 molecules of hydrogen have been added to yield the product. Next we come to the nature of oxygen atoms. First, the reaction is it gives effervescence when it reacts with sodium bicarbonate. This reaction reveals the presence of a carboxylic group. As you can see in the formula also, there are 2 oxygen atoms present, so it are present in the form of carboxylic group. Next, chemical analysis is the esterification of abietic acid. When abietic acid is subjected to esterification, it is very difficult. So this difficulty reveals that there is steric hindrance present in the carboxylic group, so making it the esterification difficult. Third reaction is in what type of carboxylic group is there. On warming with concentrated sulfuric acid, it evolves carbon monoxide. The conclusion drawn from this reaction is that the carboxylic group of abietic acid is present on a tertiary carbon. So these are the 3 reactions or chemical analysis by the help of which we reach to the nature of oxygen atoms. It is a carboxylic group and which is present on a tertiary carbon, so making the esterification difficult. The presence of carboxylic acid, it corresponds to double bond equivalent equal to 1, because 1 double bond is present. As you can see that when hydrogenation is done on abietic acid, it converts into tetrahydroabietic acid. The saturated hydrocarbon on the basis of this reaction, the saturated hydrocarbon is C19H34, which corresponds to the general formula CnH2n-4, and the class it belongs is the tricyclic. This means that the abietic acid is a tricyclic diterpenoid. Next we have to assign the carbon skeleton or the nature of carbon skeleton which is present in abietic acid. The abietic acid is again subjected to chemical analysis. On hydrogenation with selenium, sulfur or palladium in the presence of carbon, it gives a phenanthrene derivative rutene. The molecular formula is C18H18. This rutene is identified as 1-methyl 7-isopropyl phenanthrene on the basis of oxidative degradation and synthesis. The oxidative degradation was carried out in the year 1910, and this is the oxidative reduction. You can see from this chart. First, this is the rutene. This is the reaction. This is the formula of rutene. When subjected to oxidation, it forms retinoquinone, which is a dicarbonyl compound. You can see that it is converted into dicarbonyl compound, which when subjected to with reaction with KMnO4 in the presence of KOH, it undergoes benzylic acid rearrangement, resulting in the formation of this compound, which on oxidation with potassium dichromate, it converts into this dicarboxylic acid. Again, on reaction with concentrated aqueous KOH, it converts into a tricarboxylic acid. This reaction is also confirmed by the synthesis of rutene. Rutene, when subjected to Friedel-Crafts alkylation, this is isopropyl bromide. This isopropyl group adjusts at this second position, and then it undergoes reaction with succinic anhydride in the presence of aluminum chloride, again a Friedel-Crafts reaction, resulting in the formation of a ketocarboxylic acid. This ketocarboxylic acid on esterification and reaction with Grignard reagent and again hydrolysis converts into this. There is one methyl group added at this position. Hydrolysis gives this compound. This is a carboxylic acid. Then on reduction with phosphorus Hi and again the Friedel-Crafts reaction, it converts into a carbonyl group, which on Clemenson's reduction and selenium dehydrogenation yields the compound rutene. This rutene contains 18 carbon atoms. This corresponds to that. This includes that it contains a phenanthrene ring. So up till now we have reached the following conclusions. You can see that there is a phenanthrene ring present, A, B and C. We have labeled these as A, B and C. As you can see, one methyl group is present according to the structure of rutene. There is one methyl group, so we assign one methyl group here at position 4th, and at this position 13 there is an isopropyl group. So on the basis of rutene, the skeleton, we have assigned the position of isopropyl group here. Now according to this, there are 18 carbon atoms, and in abietic acid there are 20 carbon atoms. So we have to assign the position of 2 carbon atoms more to form abietic acid. As we know, it is a general fact that in sulfur or selenium dehydrogenations, carboxyl and angular methyl groups can be eliminated, or they are generally eliminated. So on the basis of this, we can assign that means that one carboxylic acid must be present. As the name indicates, one carboxylic acid is present. As we have on the chemical analysis, we have also known that one carboxylic acid is present. So this carboxylic acid might have been eliminated in selenium dehydrogenation, and in the second there might be one methyl group may be present. The probability is one angular methyl group may also be present, which have been eliminated during selenium dehydrogenation. So thus, on the basis of this hydrogenation method, on the basis of retin, formation of retin and synthesis of retin, we have come to the following conclusions. The double bond equivalent, as we know earlier, there are 6 double bond equivalents, and 2 double bonds are present in abietic acid. There is one carboxylic group present which corresponds to 1 double bond equivalent, and finally, as abietic acid contains a phenanthrene ring, that means phenanthrene contains 3 rings which corresponds to double bond equivalence 3. Thus the total of 6 double bond equivalents have been confirmed. Next, we have to assign the position of carboxylic group, the position of angular methyl group, and the position of the double bonds. So first we take position of carboxylic group, which is done by the following experiment. Abietic acid, when undergoes esterification in the presence of methanol and HCl, and yields methyl abietate with the molecular formula C19H29 COOCS3, which on reduction with sodium and ethanol yields abietanol. Abietanol on reaction with phosphorus pentachloride, it undergoes dehydration yielding a hydrocarbon methyl abietine C19H32, which on sulfur or selenium dehydrogenation it forms homoretine. This the formula of or the structure of homoretine is also can be assigned on the basis of retin, as we have seen earlier that retin contains C18 carbon atoms, and in homoretine there is 1 carbon atom extra. Both of these, retin and homoretine, when reacted with potassium ferricyanide, gives the same product, a diabasic acid, which means that one more we can, with the help of this reaction, we can assign the position of 1 extra methyl group in homoretine at this position. That means it is present in the form of this structure. 1 methyl group is, that means the ethyl group is present at position 4 in homoretine, whereas in retin it is present, the methyl group is present. So on the basis of these reactions we can come to the following conclusions. Homoretine contains 1 methylene group more than retin, and oxidation of homoretine with alkaline potassium ferricyanide gives a diabasic acid, which is phenanthrene 1,7-dicarboxylic acid. The same acid is obtained by the oxidation of this retin. So we, on the basis of this reaction, we assign the structure of homoretine as follows. The structure, as we have assigned the structure of homoretine, this can be again confirmed by the synthesis. As you can see, the synthesis is the same as that of retin. The only difference is in the presence of Grignard reagent. In retin we have taken methyl magnesium iodide, and here we take ethyl magnesium iodide, so the ethyl group is introduced here. Other steps of the reaction are same as we have seen in retin. The flow chart which we have seen here, the abietic acid and methyl abietate, we can assign the following structures on the basis of all the above reactions. As if we take the position of carboxylic acid here, and means in abietic acid, if the carboxylic group is present at this position, which is drawn this is drawn by the following reactions. So it on esterification it converts into this type of ester. Carboxylic acid converts into methyl abietate, which on reduction it converts into alcohol, as you can see, abietanol, and which on reaction with the phosphorus pentachloride it undergoes Wagner-Meerwin rearrangement, resulting in the formation of methyl abietine, as you can see here. And finally this methyl abietine on dehydrogenation with sulfur, it forms homoretine of the formula C19H20. Thus if we assign the position of carboxylic acid at position 4, all the reactions of the above flow chart can be explained. So the carboxylic group is present at the position 4th. Next we assign the position of angular methyl group. The abietic acid is again subjected to a series of chemical reactions. As you can see here, abietic acid as on oxidation with potassium permanganate, it results in the formation of 2 dicarboxylic acid, as you can see these 1 and 2, A and B. These two acids on oxidation, it converts into this type of dicarboxylic acid, and then finally on further oxidation this type 2-methyl glutaric acid is obtained. The formation of two acids, as you can see, it is possible only if they are derived from the ring A of. Ring A is intact in both these cases, and the formation of these 2 carboxylic acid indicates that ring B and C contains unsaturated or it contains double bonds. Because of this, the 2 carboxylic acids have been obtained on KMnO4 oxidation. This carboxylic acid is already present in abietic acid, and these 2 carboxylic acid, as you can see in the 2 these two here or here also, these 2 carboxylic acids results as a result of oxidative degradation of double bonds. They again on these tricarboxylic acids on selenium dehydrogenation, one forms 1,2,3-trimethylbenzene, whereas the other converts into metaxylene. The formation of these 2 compounds indicates that the methyl group is present or the meta position to each other. So on the basis of following reactions, we can derive at the following conclusions. 2 acids A and B are derived from ring A of abietic acid. Ring B and C, being unsaturated, are expected to cleave during oxidation. That means the double bonds are not present in ring A, but they are present in ring B and C. This is ring A, this is ring B, and this is ring C. The isolation, third very important conclusion, the isolation of metaxylene and 1,2,3-trimethylbenzene indicates that methyl groups are in meta position. So as you can see, 1 methyl group, we have already assigned the position here. 1 methyl group arises from this oxidative degradation. Here this one methyl group, and the third one may be, this is the position of angular methyl group. Here it is. Similarly, in tricarboxylic acid C, you can see this has been in selenium dehydrogenation. This carboxylic acid has been removed. Here also this carboxylic acid has been removed. So 1 methyl group at position this one, and the other methyl group must be, the most probable structure is this methyl group, angular methyl group. The formation of both these, the isolation of metaxylene and 1,2,3-trimethylbenzene, indicates that methyl groups are in meta position. So the conclusion drawn is that this methyl group, as you can see here, the position of the angular methyl group is at carbon 10. We have derived the following conclusion: the methyl group occupies position 10 on the basis of the following products obtained from selenium dehydrogenation. Final is to assign the position of double bonds. Up till now we have assigned the position of carboxylic group, and we have assigned the position of angular methyl group. Next, last is the position of double bonds. This can be achieved by the following reaction. It forms an adduct with maleic anhydride. As you can see, when it undergoes when abietic acid was subjected to Diels-Alder reaction, it forms a Diels-Alder adduct. The same Diels-Alder adduct was obtained from levopimeric acid, the structure of which was already known to the scientist. So both the structures were same, and both the structures of scientists were actually, with the reaction, the scientists were at first puzzled. They thought that the structures are the same, or they can't reach to any conclusion with the help of this reaction. That means this reaction was misleading. But afterwards, after further investigation or chemical reactions, they reached the following conclusion that the structure of abietic acid was different from levopimeric acid, and the possibility is that it undergoes isomerization at 100 degrees centigrade, abietic acid, and it converted into levopimeric acid, which on Diels at a reaction form the same product as the levopimeric acid. To confirm the structure of abietic acid, it was done with the help of UV spectroscopy of Woodward-Fieser rules. When the spectra was obtained, the abietic acid, the lambda max, came out at 238 nanometer, whereas the lambda max of levopimeric acid was at 272 nanometer. This means that the two compounds are totally different on the basis of UV spectra. As you can see from the Woodward-Fieser rules, the homoannular diene, the base value is 253 plus the increments which are to be added, as we all know. The second as the heteroannular diene, and for heteroannular diene the base value is 214 plus we have to add the increments to get the value of lambda max. As you can see, the value of lambda S max is small as compared to the lambda max of levopimeric acid. Finally, we already know the structure of levopimeric acids, and the double bonds are present at this position. This means this is a homoannular diene. But on the basis of lambda max, we reach to the following conclusion that the abietic acid contains a heteroannular diene because the lambda max value is 338. So we reach to on the basis of UV spectra, we reach to the following conclusion: abietic contains conjugated double bonds and it is a heteroannular diene. This is very important conclusion derived, which confirms the structure or which differentiates the structure of abietic acid from levopimeric acid. Finally, the confirmation of the position of the conjugated double bonds. The following very important reaction has been carried out. When abietic acid is subjected to KMnO4 oxidation or oxidative degradation, we get isobutyric acid as one of the products. Plus the other products, we have to concentrate only on the isobutyric acid. This isobutyric acid gives very important information about the structure of the abietic acid. It indicates that this conversion of this carboxylic acid can be formed from KMnO4 oxidation only with the possibility is that if the double bond is present adjacent to or adjoining to this isobutyl group, as you can see. So the probability of one double bond is either it occupies this 12-13 position or it occupies 13-14 position. So the conclusion is that the presence of one double bond is in ring C because the isobutyl group is present in ring C. We have already assigned it the position 13. So the possibility of one double bond is either at 13-14 or at 12-13. Now we have to assign the position of the next double bond, as there are two double bonds present, keeping in view that abietic acid is a heteroannular diene. So the various possibilities of you can see, if we assign the position of double bond at 12-13, then the next conjugated double bond can be present at the position there, and or it can be present here. So there are three possibilities, but there are two possibilities here, and you can see both the possibilities. There is a formation of homoannular diene. This cancels the following reactions of the following structures of abietic acid. Or secondly, we can assign, if we assign the position 13 or 14, the next position of the double bonds can be either 11-12, which again forms the homoannular diene, or it can be at 8-9 position, again forming a homoannular diene. So the only possibility of the double bond is 7 and 8. in abietic acid, resulting in the formation of a heteroannular diene. So the position of, you can see there is conjugated double bond here, and a heteroannular ring is present. One double bond is present in B and the other double bond is present in D, which also justifies the chemical reactions which we have studied so far. So finally the structure of abietic acid is this. The carboxylic group is present at position 4th. One methyl group is present at position 4th. Angular methyl group, very important, at position 10. Isopropyl group is present at the position 13, and the double bonds are conjugated in nature and they are present in one in ring B at 13 positions and the other is in 7th, 8th positions. So while dealing with these reactions, the very important is to assign the very important points, as you can see here. One is the position of carboxylic acid, very important from the examination point of view. Secondly, the position of angular methyl groups, and third is the position of double bonds. Thank you.